So, you want to learn everything there is to learn about moments. Whether you're an A-level physics student or an A-level math student, or you're just a neek who does IB and you're a bit scared of university, moments can be a bit tricky, but I think they're one of those things that get introduced quite quickly, and students aren't as prepared, and so they think it's tricky when actually it's not. Now, my name's Rayhan Baig, I'm a second year math student at Imperial College London, and truthfully, I'm a bit of a moments neek. And after this presentation, there's really three things I want you to know about moments. One, what is a moment? Two, how can I do calculations with moments? And three, we'll do some practice problems as well. Now, when you open your paper in May or next year, or in like 10 years if you're a complete prodigy or whatever, you're going to open your paper and you're going to see something pretty tricky. It'll probably look something like this. There'll be forces flying around and distances and weird fingers and this weird contraption that no one ever really uses anymore. And you'll be forced to try and figure something out, even if you're really stuck. Now, this is one of those cases where you need to know moments. And actually, even though it looks pretty tricky right now, hopefully I'll convince you that it's actually not that hard at all. So, first things first, what is a moment? A moment is the turning effect of a force. This is going to be our key definition for everything we're about to do. A moment is the turning effect of a force. Now, hopefully, unless you're completely useless, you know what a force is. It's a push or a pull, and it's measured in newtons, but you may not be as certain about what a turning effect is. So let's look at an example. Let's say you're a strapping young man like yourself, and it's Valentine's Day. You've just made your way over to the park, and unfortunately, you don't have anyone as your date to play with. And so you're just sitting on the seesaw alone, and you weigh 50 newtons. Now, I think we can all tell, maybe from experience, that you're going to go flying down, and the seesaw is going to tilt upwards, specifically anti-clockwise. Now, let's change it up a bit. Let's say you got a bit luckier, and actually you do have a date to go with. Unfortunately, she's a bit of a UK beast, and she weighs 80 newtons. So I think now we can guess that actually what's going to happen is the seesaw is going to tilt downwards or clockwise in her favor, and we're going to go flying up. But it's not as simple as just saying that it's going to always tilt in favor of the heavier side. Because in this example, as you may know from when you're trying to turn a door, or if you've ever seen a lever in real life, it also matters the distance away you are from the pivot point, or the point that we're balancing on. So in this case, even though we are lighter, we're way further away from the pivot. So we're going to be able to generate a much bigger turning effect than she is right now, because she is much closer. And so that kind of gets us to start to think that it's not just the weight that matters, it also matters the distance we are away from the pivot. And so there's really two things that matter here. The magnitude of the force, which is which side is heavier, is it left or right, and the distance away from the pivot, being close versus being far. And specifically, we're talking about the perpendicular distance. And I'll talk in a minute about what the perpendicular distance away is, as opposed to just the regular distance that we could talk about. So there's really this magic formula. Moments is equal to force times distance. Distance measured in meters, force measured in newtons. And so the moment should be measured in Newton meters. And again, we have this note that we're really talking about the perpendicular distance from the pivot here, not just any old distance. And I'll talk a bit about what that means in a second. But let's go back to our example. So here we should really start to put some numbers towards this thing, because we've got a formula now. We can see which side is going to generate the most overall moment, which is the direction that it's going to tilt in. So let's put some numbers to it. The moment from you is 50 newtons multiplied by 0.4 meters, which comes out to 20 newton meters. The moment from her is 80 newtons multiplied by 1.1 meters, which comes out to 88 newton meters. And so now you may want to think, oh, are we going to subtract? Are we going to add? Well, actually, they're going to cancel out a bit, because the turning effect one way is going to cancel out the turning effect the other way. And so overall, we have 68 newton meters clockwise. So now let's talk a bit about that perpendicular thing I was talking about earlier. So let's say your date-to-be is trying to impress you, and she's doing some weird calisthenics thing off the end of the bar. I mean, it looks pretty impressive, but it definitely changes things, because now the direction of the force is not acting perfectly perpendicular to the plank or the seesaw. It's now acting at an angle, specifically a 47-degree angle here. And so our perpendicular distance in the previous example was 1.1 meters, but now it's changed to this x. And we're going to have to use trigonometry or something to try and figure out what this x is, because the angle of the force has changed, and so the perpendicular distance away from the pivot has also changed. And now I want to talk about when exactly we're going to need moments. So pretty much any equilibrium problem you're going to see on the exam is going to be in terms of moments. And the key principle to remember is that if a system is in equilibrium, then the resultant moment is zero. And this means that the sum of all the clockwise moments is going to equal the sum of all the anti-clockwise moments. They're going to come together and cancel out. So previously, you may have just considered upwards and downwards forces, leftwards and rightwards forces, and equaling those together. Now we get an extra element to play with, that the resultant moment about any pivot must be zero. And this pivot point could be anywhere. It just so happens that it's very obvious where the pivot point we're going to do our calculations from are, because it's going to be the thing that the whole thing balances on. But it doesn't have to be that. It could be any point. So In this case, the anti-clockwise moment, which is the moments generated by us, is still 20 Newton meters, but now we don't actually know the weight of the woman on the other side, and so we need to calculate this. And how are we going to calculate it? Well, we're going to use the formula that we had earlier, that the sum of the clockwise moments is going to equal the sum of the anti-clockwise moments. The sum of the clockwise moments is 1.1x, the sum of the anti-clockwise moments is 20, so equal those together, and then we get that x is equal to 18.2. So it actually turns out you weren't dating a woman at all, you're actually dating like a pure basmati rice object thing, because I don't know of any woman that's able to generate only 18.2 newtons. So in the previous slide, we talked about sums of moments. So let's say you decide to cheat on your pure basmati rice state and you brought some Lidl deluxe basmati rice instead. You can collect all of the moments on one side and equal them to all the moments on the other side. So in this case, the clockwise moments all come out to 20 Newton meters and the anti-clockwise moments come out to 16 plus 3x. Equal them together, slip that bow, and you get x is equal to 1.33 meters. So now going back to the weird example we saw at the beginning, as you can see, it's actually not that tricky at all. I mean, obviously you've got this weird diagram in the middle to kind of distract you, but if you can avert your gaze a little bit and just zoom out, all we need is that the moment is equal to force times perpendicular distance. What is the force in the question? Well, it's the force x. What is the perpendicular distance away? It's super easy. It's just 48 millimeters. So moment is equal to 250 newtons. Now, if you can speed read, you should see in the question that they give us the magnitude of force x is 250 newtons. The perpendicular distance is 48 millimeters. You put that into standard units by multiplying by 10 to the power of minus 3, and you get 12 newton meters. See? Pretty easy. And now if you want to give yourself a challenge, you can try and think, can you find the magnitude of y using what we discussed about the sum of clockwise and anti-clockwise moments. But that's all for today. Make sure to like, follow, subscribe, and keep doing past papers.